So welcome to this lecture series. In this lecture series, we are going to discuss about complex numbers. We begin from the definition of a complex number, and then the operations which involves complex numbers. And the motivation on discussion about complex numbers originates from when you're solving polynomial equations, especially quadratic equations, whereby the discriminant turns out to be a negative number. And when you define the square root of negative numbers, when you are dealing with real numbers, you get a math error, or simply the square roots of negative numbers are not defined in R. So when we are faced with such problems of solving quadratic equations, whose the discriminant turns out to be a negative number, the set of complex numbers comes in handy to solving such kind of problems. So problem of complex numbers or discussion on complex numbers has many applications, especially in modeling quantum waves in physics, and also representing alternating current in problems of electrical engineering, and many more other applications. So we'll start by defining a complex number and give a few definitions. And then later on, we'll discuss about the operations on complex numbers, and then also state and see how we can use the Moivre's theorem to find powers of complex numbers and also roots of complex numbers. So let's get started. And I have to make it very clear from the start that the term complex numbers doesn't necessarily mean that when you're studying this set of numbers, things are going to be very hard for you to understand. It's only that it's a name used to specify those special kind of numbers. But there is no, in any way, relationship between the vocabulary complex and the number that we're going to discuss in this set of numbers. So from the start, don't be scared by the term complex numbers, because it is just a name we give to those special kind of numbers. Does not necessarily mean that it is very hard to understand the concept of complex numbers. So let's begin by defining a complex number. And then after defining a complex number, then we'll later on deal with operations on complex numbers. So a complex number is any number that can be written in the form a plus bi or x plus b, x plus yi, where x and y are real numbers. So a complex number is any number that can be written in the form x plus iy or x plus yi, where x and y are real numbers and this letter I is a value of square root of -1. So that's how we define a complex number. For example, a number like 1/2 plus 3i, 6 minus 2i, 8 plus 11i, say 17 minus I, 18 plus 16i, root 2 plus pi I, etc. All these are examples of complex numbers. Then we can collectively define the set of complex numbers. So the set of complex numbers denoted by bold C is defined as or we can say defined by. So the set C is the set of all numbers of the form x plus iy such that x and y are real numbers and I squared is equals to -1, or simply square root of 1 is I. So this is how we define the set of complex numbers. So if you remember from our previous discussion, we said that real numbers are simply rationals or irrational numbers. So for example, this, we have, say, I have 1, 5, say √3, √2, 10, -50, etc. So these are examples of real numbers. So we can see that a number like a half, which is a real number, can be written as a half plus 0i. When you write a half as a half plus 0i, then this form is in agreement with what we are saying, that a number that can be written in the form x plus yi, where both x and y are real numbers. So 0 and a half are real numbers. So when you view a half as a half plus 0i, then this becomes a number in the complex set. So similarly, a number like, say, 10 can be written as 10 plus 0i. And when you write in this form, then that takes the form of definition of a complex number. So we can in general say that all real numbers are simply complex numbers, because every real number can be written in the form x plus yi, where both x and y are real numbers. So we can say all real numbers are complex numbers. And then to appreciate the structure of complex numbers, let's consider this. Consider the quadratic equation ax squared plus bx plus c equals to 0. So then we know that from quadratic formula, the quadratic formula, the solution is given by x equals to minus b plus or minus square root of b squared minus 4ac. You divide by 2a. This we know from our Form 3 work, that to solve a quadratic equation of this form, x is given by this formula, minus b plus or minus square root of b squared minus 4ac, everything divided by 2a. And then if we recall from what you did in Form 3 work, we remember that the number under the root sign is called the discriminant, or the expression under the root sign is called the discriminant. So the expression b squared minus 4ac under the root sign is called the discriminant. Then the solution of the quadratic equation depends on the value of the discriminant. Depends on this expression b squared minus 4ac, the so-called discriminant. And so depending on the value of the discriminant, we will be able now to classify the solutions of this quadratic equation. So there are three cases to consider. If you remember what we already done in high school, that case one is when this discriminant is a positive number. So case one, if b squared minus 4ac is positive, that means greater than 0, then there are two distinct real roots. So the quadratic equation will have two solutions, both of them whose value will be real numbers. And then case two, if b squared minus 4ac is identically equals to 0, then there are two equal real roots. And then case three, if b squared minus 4ac is less than 0, that simply means it's negative, then there are no real roots. So when the discriminant is negative, then you will not get a real number when you get the square root of a negative number. And so that is actually what motivates us to discuss this special set of numbers called the complex numbers. So in this case, we can always find the solution in all the cases by extending the numbers, extending the number system to include definition of square root of negative numbers, starting the square root of -1. So then because there is no real number, that squares to get -1, a number minus square root of -1 is called an imaginary number. Usually expressed as I. Sometimes other authors give it small j, but in most cases we'll be using I to represent imaginary number of the imaginary unit. So complex numbers have a real part and an imaginary part. And maybe we can formally give that definition of what we call a real part and imaginary part of a complex number. And give in form of a definition. So definition that lets z equals to x plus iy be a complex number x is called the real part of z denoted by while y is called the imaginary part of z denoted by so that's what we have. So for example, when you are given a number z equals to 6 plus 10i, then the real part of this number will be 6, and the real part, the imaginary part of this number will be 10. So that's what we have. And if we have, for example, another number z equals to x plus 3y plus a sine x I, then the real part of z will be given by x plus 3y, while the imaginary part of z will be given by a sine x. So it's very simple that there are two parts of the complex number. The part without the imaginary unit I is called the real part, while the part or the coefficient of imaginary unit I is called the imaginary part of Z, complex number Z. So note that in a complex number, the real part and the imaginary part cannot be combined to form a single term. That means that those real parts and imaginary parts are independent. That for any complex number, the real part is independent of the imaginary part. Having appreciated the definition of a complex number, then we can have this. Write each of the following terms the following in terms of the imaginary unit I. So for example, we have square root of -1, B square root of -4, C square root of -16, D square root of -28, and say E the square root of -64. So the main appreciation on how to reduce this is to write the number under the root sign as product of two numbers, where one of them will be -1 and the other one will be a positive number. Then now define the usual square root. So the first part of the first question in this example is obvious that this is what we are saying is the definition of I. So square root of -1 is I. And then this one, we write it as square root of 4 times -1, because 4 times -1 is still -4. And then you remember from your knowledge on laws of indices, square root of product of two numbers A, B, the same as square root of A times square root of B. So this turns out to be square root of 4 times square root of -1. And square root of 4 is plus or minus 2. Square root of -1 is I. So square root of -4 is the same as plus or minus 2I. Similarly, this will write it as 16 times -1. Then using this property, we'll have square root of 16 times square root of -1. And the square root of 16 is plus or minus 4. Square root of -1 is I. So root -16 is the same as plus or minus 4I. Then this is the same as square root of 28 times -1, the same as square root of 28 times square root of -1. And square root of 28 is plus or minus 2 root 7, then times I. This will be the same as square root of 64 times -1, which will write as square root of 64 times square root of -1. Root 64 is plus or minus 8. Then root 1 is root of -1 is I. So this will be plus or minus 8I. So that's how we simplify roots involving negative numbers. You just write the root or write the number under the root sign as a product of two numbers where one of the number is positive then the other number is -1. Then you remember that square root of -1 is I, then you simplify accordingly. So let's also see how the I number behaves when we put it to some arbitrary powers. So for example, we know that from definition, I squared is -1. Then if I say I power 3, if I want to get the value of I power 3, the best way to do that is to rewrite I power 3 as a product of lower powers of I. So I power 3 can be written as I squared times another I. And because I squared is -1, so I'll have -1 times I, and -1 times I, I'll get -I. And then the other thing is that I can also define I power 4, and I power 4 is the same as I power 3 times I. Using laws of integers, you know that I power 3 times I is the same as I power 4. Then from the previous step, I power 3 is minus I. Then I multiply by this I. So minus I times I is minus I squared. But remember, I squared is -1. So -1 times -1, I get +1. Then I power 5 is the same as I power 4 times another I. And from our previous working, I power 4 is 1. Then you multiply by I, and 1 times I just get I. So the value of I power 5 is the same as I. Then I power 6 is the same as I power 5 times I. So which is the same as I power 5 reduces to I from the previous working times this I. And I times I will give me I squared. And I squared is the same as -1. Then let's define I power 7. I power 7 is the same as I power 6 times I. And from the previous working, I power 6 is -1. Then I multiply by I. So this will give me -I. Then I power 8 is the same as I power 7 times I. And I power 7 is -I. I multiply by I. So this gives me -I squared. But -I squared is the same as -1 times -1, which is +1. So the value of I power 8 is 1. Then I power 9 is the same as I power 8. I multiply by I. But I power 8 is 1 from the previous step. So I multiply by I. This just reduces to I. Then I power 10 is the same as I power 9 times I. So I power 9, we have gotten the answer is I times I. This will be I power 2, which is -1. Then I power 11 is the same as I power 10 times I, which will be -1 times I, and this will give us -I. Then I power 12 will mean I power 11. I multiply by I, which will be -I times I, which will give us -I squared. And you know I squared is -1, so -1 gives us +1. Then I power 13 will be I power 12 times I, which is 1 times I, and this is just I. I power 14 is I power 13 times I, which will be I times I, to give us I squared, whose value we know is -1. Maybe let's go up to 16, and then maybe we can stop there and see what's happening in general. I power 15 is I power 14 times I, which is -1 times I, and this would be minus I. Then I power 16 is the same as I power 15 times another I, which is minus I times I. And when this will be negative I squared, and the answer will be positive 1. So when we stop there and we make some observation on what is happening, we realize that whenever the power of I is a multiple of 4, we get 1. You see that here, I power 4 gave us 1. I power 8 gave us 1. And then I power 12 also gave us 1. And then I power 16 is also giving us 1. So in general, I power k will give you 1, provided k is a multiple of 4. And so you can be given higher powers of I to reduce them to smaller values of I or 1. For example, I power 49. If someone asks you to evaluate I power 49, you simply express 49 as a product of one number, which is a multiple of 4 close to 49, or slightly less than 49 itself. So they're the same as I power 48 times I. And I power 48, we know that 48 is a multiple of 4. So it's the same as I power 4 power 12, then I multiply by I. And we have said that I power 4 is positive 1 power 12, I multiply by I. And we know 1 raised power any power is the same as 1. And so 1 times I is just I. So I power 49 is the same as just I. I power 103, you just write find a closest multiple of 4 to 103, and that would be 100. So this can be written as I power 100 times I power 3. And you know 4 divides 100 25 times. So this is the same as I power 4 raised power 25. I power 3 can be written as I squared times I. And we know that I squared is minus 1. So this is the same as 1 power 25 times minus 1 times I. 1 power 25 is 1 minus 1 times I. And this will just give us minus I. And when you're asked to say, maybe find the value of 2I power 5, then it's the same as 2 power 5 times I power 5. Because you remember from laws of interest that AB power n is the same as A power n, B power n. So 2 power 5 is 32. Then I power 5 is the same as I power 4 times I. So this will be 32 times I power 4 is 1 times I. So this just gives us 32I. And then another example involving simplification of powers of I. It can be this, find the value of the expression 1 plus I power 10 plus I power 20 plus I power 30. So the beauty with these powers is that all of them are even numbers, and you know that I squared is -1. So to solve this, we write this one as 1 plus. So write it as I squared raised power 5. And then this other, write I squared raised power 10. And then this I squared raised power 15. We're just making use of the laws of indices that a power m power n is the same as a power m n. Then this will give us 1. I squared is minus 1, so power 5 plus minus 1 power 10 plus minus 1 power 15. And you know from high school that minus 1 power n, it always has two values. It's positive 1 when n is even, and is negative 1 when n is odd. So that's what negative 1 power n gives. So this means that we'll have 1 plus, since 5 is an odd number, then minus 1 power 5 is minus 1. And then plus, since 10 is an even number, minus 1 will be positive 1. Plus, since 15 is an odd number, minus 1 power 15 will be minus 1. So this will give us 1 minus 1 plus 1 minus 1. And this will be 1 plus 1 minus 1 minus 1. And this is 0. So the whole of that expression is nothing but 0. But then lastly, on the same, if we have express 8i cubed plus 6i power 6, I alone is what is raised to power 16. Six I power 16 minus 12i power 11 in terms of in form a plus bi. So this 8i power 3 plus 6i power 16 minus 12i power 11 in the form a plus bi. So solution, you write this one as 8i squared times I, and then plus 6i power 2 raised power 8 minus 12i power 10 times I. Then this will be the same as 8 minus 1 times I plus 6 minus 1 power 8 minus 12 minus, this will give us actually, I can write this one as I squared power 5 times I. So the first part will give me 8 minus 8i. Now minus 1 raised power 8. 8 being an even number, then it makes me to have positive 1. So I have 6 minus 12. Now I squared is minus 1. And then when I raise minus 1 to power 5, I get minus 1 because 5 is an odd number. So minus 1 power 5 times I. So this will be minus 8i plus 6. Now minus 1 power 5 is minus 1 times minus 12. I get positive 12. Then I. So collecting real parts and imaginary parts, will have 6 minus 8i plus 12i will give us 4i. So this will be the reduced expression for that given problem. So in the next session, we will be discussing how to carry out different operations on complex numbers. I will discuss how to add, multiply, find the difference and product of complex numbers. Thank you.